This is the second video on designing an image classification model using the Fashion MNIST dataset. Following the first video, I will explain the model design part and review the results of training and testing the designed model. After applying a convolutional layer to the model, we proceed to apply batch normalization. This helps normalize the output from the convolution layer, smoothing the loss function surface and stabilizing the training process while enhancing speed. It also prevents overfitting, helping the model generalize better. Thus, we insert batch normalization layers between functions here, here, for improved performance. Okay, so next we again apply a convolution layer followed by batch normalization, this time increasing the number of filters to 32. Then we perform dropout. Okay, I'm gonna change the color of a highlighter. Dropout. Dropout randomly removes a certain percentage of hidden units, helping to prevent overfitting and reducing test set errors. Here we set the dropout rate to 0.2, meaning there's a 20% chance that a hidden unit will be dropped. We repeat this process and finally increase the filters to 64. Next, we perform dimensionality reduction using a max pooling layer to prepare the data for the dense layers. Max pooling reduces the spatial dimensions of the feature maps by selecting the maximum value in each 2 by 2 region. This makes the model more computationally efficient by reducing the data size. After max pooling, we flatten the output into a 1D array. This step is necessary to connect the convolutional layers to the fully connected layers that follow. Okay. Finally, we move to the dense layers, which perform the actual classification based on the features extracted by the convolutional layers. This fully connected layer consists of 512 neurons and uses the ReLU activation function. It combines the learned features into more abstract representation. And batch normalization again, normalizing the output of this layer improves training stability. Well, the final layer contains 10 neurons, each corresponding to one of the 10 output classes. The softmax activation function is applied here to convert the outputs into probabilities that sum to 1. Now we have completed the model building process. So let's check the model we've implemented. By using summary, we can see the output shape and the number of parameters for each layer stacked in order. Once everything looks correct, we can proceed with model compilation and training. As you can see, we set the optimizer to atom, the loss function to sparse categorical cross entropy, and the evaluation matrix to accuracy. Then we train the model using the training images and labels. This process took a bit longer than expected, so I set the epochs to 5. You can check the results of each train, the loss and accuracy here. Now, let's test the model we've trained. Upon checking the size of the actual test dataset, we see that there are a total of 10,000 samples. After training on 60,000 images, we'll evaluate it on these 10,000 test samples. After evaluating the model using the evaluate function, I found the test loss to be around 0.27 and the test accuracy to be 0.91, which is about 91%. To explain these figures, the loss represents the difference between the model's prediction and actual values. It's a numeric representation of the model's overall performance. A lower loss indicates that the predictions are closer to the actual values. Of course, since both loss and accuracy are satisfactory, we can evaluate the current model's performance positively. However, we will also need to consider strategies for further improvements, such as data augmentation, model architecture adjustments, and hyperparameter tuning to reduce the loss even further. Okay, so now let's visualize the prediction results based on the above information. We'll use the predict function to generate a list of prediction results stored in the predictions variable. I will take a total of 9 images arranged in a 3 by 3 grid and retrieve their here predicted label and true labels. If the two values match, then the output will be in green. If they differ, it will be in red. So, as you can see from the results, all the predicted labels are displayed in green, right? Confirming that all 9 predictions were correct. So, that's how we used a CNN model to classify the Fashion MNIST dataset. In the future, I plan to work on adjusting this model to improve its performance even further. Thank you for watching my video on implementing this model. Bye-bye.